Yeah, hello, myself Maruti, welcoming you all to this physics video session. In this video, I'm going to explain how, Pauli's exclusive principle has helped out in knowing how the electrons should be filled in the orbit, orbital. Right. So that is what? It is nothing but electronic configuration. Distribution of electrons in shells, subshells and orbitals of an atom is nothing but electronic configuration. That's cool. Right. If you think about the nucleus, right, if you are having the orbits, this is the first orbit and this is the second orbit, whatever. How the electron should be filled in the orbit. First we have to think about the orbit, then the subshell in that one, later on the orbitons present in that one, how that electron enters into the orbit, of the subshell, of the orbital, how the electron enters inside, in what is the procedure it has to be followed. That is explained by distributive or the distribution. It is nothing but electronic configuration. Of course, if it is uni-electronic spectrum, there is no issues. But if it is a multi-electronic spectrum in which there are many electrons, then there should be followed certain procedures. Alright, which orbit has to be filled first, basing upon the energies, basing upon the principal quantum number, basing upon the azimuthal quantum number, especially basing upon the energies. Right, the orbital which is having less energy should be filled first according to Hubble principle or whatever. In the same way, there are certain rules, right? So as the rules are saying how the electrons should be filled in the multi-electronic elements, we are going to know. Multi-electron system is also called as poly-electron system. Okay, so the three main principles are Pauli's exclusive principle, Hubble principle and Hund's rules. These guys, these principles will tell us how to fill the electrons in the system. Now, in this video, I'm going to talk about Pauli's exclusive principle. It's a beautiful one. What he says, you take any two electrons of the atom, no two electrons will be having all the four quantum numbers same, right? What are the four quantum numbers? Just we know n is nothing but a principal quantum number, right? Next, L is nothing but azimuthal quantum number. ML is nothing but magnetic quantum number, and MS is nothing but spin quantum number. Right? If you take any two electrons of the same atom, example, let us go for oxygen. Oxygen, you know, atomic number is 8. Right? We are having 8 electrons in that. 1, 2, 3, 4, 6, 7, 8. 8 electrons are the an example, negative. Of course, we have 8 positives also. Right? This is the first one, second one. In the same way, it is going on till 8th one. You take any two electrons. It might be the second electron, or it might be the 8th electron. Right, the second electron or the 8th electron. If you check all the four values, right, N, L, ML and MS, they are not having all the four quantum numbers the same. Any one will be varying. Probably 3 might be same, no issues. 3 might be same, but 1 will be different. That is what Pauli's exclusive principle says. No two electrons you compare, of course, of the same atom. Don't compare with the other atom. Right? Of the same atom, if you compare any two electrons, at least one will be different of all the four. That's what Mr. Pauli's exclusive principle has done. Well, let's come back to the video now with the help of an example explaining or verifying Pauli's exclusive principle. Alright, now the example what I have taken is nothing but helium atom. Alright, you know helium atom, the symbol is, the helium atom is nothing but H2. Okay, I have considered helium atom. Now, what's the atomic number of helium atom? It's nothing but atomic number Z is equal to 2. Okay, so as we are saying that atomic number is 2, if we fill it out in a structure, right, if this is the nucleus, if this is the K orbit, N is equal to 1, right, so if we are talking about 1s, right, the condition is both the two electrons will be present inside the oneness orbital. That's what. Number of electrons. How many electrons it has? Number of electrons it has is 2. Okay, now how to mention the electronic configuration? Electronic configuration, as you all know, we are supposed to mention in the terms of NLX, right? NLX. Now, N is nothing but which shell? It is nothing but K shell, right? So as it is K shell, the shell what we are taking is nothing but K. Now, the subshell into which the 2 electrons has went in is nothing but S. Okay, now by taking the value of K and by taking the value of S, we know the principal quantum number for that one is S. Therefore, as the N is nothing but principal quantum number, as it is 1, we take it as 1. The subshell what we are using is nothing but S. Therefore, S. And the X is nothing but the number of electrons. How many number of electrons are there? It's nothing but 2. Okay, so we have taken in a helium atom, symbol H2, atomic number 2, and number of electrons is nothing but 2, and electronic configuration by using the short notation NLX, we got first orbit, S subshell, and 2 electrons are there. As I said, shell is nothing but K and subshell is nothing but S. We got the complete details of that one. Now, how we are filling that one, right? What Mr. Paulis has said, that no 2 electrons of the same atom will have all the 4 quantum numbers the same. Right, how many electrons we have? We have 2 electrons. Right, how they are entering? Let us match up all the 4 quantum numbers. What are the 4 quantum numbers what we have? It's nothing but N, which is nothing but the principal quantum number. L is nothing but azimuthal quantum number. ML is nothing but magnetic quantum number. And the next one is spin quantum number. We are having 4 quantum numbers. So let's check all the 4 quantum numbers. First, the 2 electrons which are present, the first electron and the second electron. Let's work on that one. Now, if you check it out, as N, as it is shell is K, what's the N value? It's nothing but K shell, as you have seen, right? As you all know, N value for that one is nothing but 1. The first electron enters into principal quantum number is nothing but 1. Why? It's nothing but the K shell. If it is K shell, N value is 1. We have taken. Now, the second electron is also in the same orbit, the same K orbit, K shell. Therefore, the principal quantum number of the second electron is also 1. Fine. Means, right, one of the quantum numbers of both the electrons is already same. Right. But what is Pauli saying? No 2 electrons will have all the 4 quantum numbers same. Right. Any one will be missing. Right. Any one will be mismatched. But here, for the first electron, principal quantum number is 1, and for the second electron, principal quantum number is also 1. Means it's matching. Okay, there are left over with 3. Any one should be mismatched. Now, let's get for the principal, right, azimuthal quantum number or angular momentum quantum number. Angular momentum quantum number depends upon principal quantum number, right? So, what is the subshell it is? It is nothing but S subshell. S subshell we are entering. Right, so we know, right, L subshell is dependent upon N value, right? We know, right, it goes till N minus 1. N minus 1. Here, what is N value? We know it goes on from 0 to N minus 1. Okay, what's the N value? N value is nothing but 1. 1 minus 1, right, it's nothing but 0 here, right? So, for L value is nothing but 0 for the first electron. In the same way, again for the second electron also, again the N value is 0. So, if you plug in 1 in the place of N, 1 minus 1, again we are getting 0. Yo man, right, means second quantum number also matched for both of them. What Pauli's exclusive principle says, according to the Pauli's exclusive principle, no 2 electrons will have all 4 quantum numbers same. 4 quantum numbers same. This is the condition. Any one should be mismatched. We have checked 2. Both are matching. Right? Both are matching. Okay, let's go for the third one. Third one. This is nothing but magnetic quantum number. Again, magnetic quantum number is dependent upon. Here I said azimuthal quantum number is dependent upon principal quantum number by the value of N minus 1. Right. Again, magnetic quantum number is dependent upon the azimuthal quantum number. You know, right? ML is equal to 2L plus 1. This is the value what we are planning to. Right? Means again, this is dependent upon azimuthal quantum number. So, for the first electron, what is the azimuthal quantum number? 0. Let us plug in 0 for that. That is 2 into 0 plus 1. It's nothing but 1. Come on, man. Again, let's go for the second electron. Second electron, what is ML value? Magnetic quantum number value. Again, it is dependent upon this. Let's plug in 0. 2 into 0 plus 1. Again, we are getting 1. There, what the surprise here. For both the electrons of helium, right, magnetic quantum number is same. Magnetic quantum number is same. Azimuthal quantum number is same. Principal quantum number is same. But what Pauli says, that no two electrons should have the same quantum number, right? Something should be mismatched. Here everything is matched. Now let's go for the only alternative present over there. So that is nothing but now it is having two spins, right? If you are thinking about that orbital, right? If you are thinking about that, so what kind of spin it has? It will be having two different direction spin. That is what the matching, right? The ms value of the first one is nothing but plus half for the first electron, and for the second electron it is nothing but minus half, right? So the first one is nothing but you indicate it with the right, you indicate like this, and the second one will be indicated like this, right? So the next one, it's nothing but a clockwise direction. It's nothing but anti-clock. So this is the difference. This is the difference. Here everything is matched, but here they are having different half integral values, half integer values. The spin quantum number of the first electron and the second electrons are right not matching. So because of that the electrons present, one is moving in the upward direction, the other is moving in the downward direction. Because of this, we call that one, what is the kind of spin it has? It is nothing but anti-parallel spin. Parallel spin. What does it mean? They are moving in different direction. They are in different directions, right? That is what we have to remember. So what we have observed, though all the three quantum numbers are say here m value, right, n value, principal quantum number, azimuthal quantum number, and magnetic quantum number are same, right? Only what is differing? Only magnetic spin quantum number, half integral value is differing. So this is what Pauli's exclusive principle says. Whatever might be the electrons present in the same atom, any one of the quantum number will be mismatched. All the four quantum numbers won't be same for any two electrons in the atom. This is the proof. This is the procedure explained by Mr. Pauli's. Of course, it has certain defects. Yeah, the major consequences of Pauli's exclusive principle is nothing but electron occupancy, right? So what does it mean? Means as any two ms values, how many values ms has? Ms is having, it's nothing but the spin quantum number values of any, we are having only plus half and minus half, right? Moving one in the clockwise, the other one in the anti-clockwise. What does it mean? Means, right, any electron can hold only two electrons, one in the clockwise direction and one is in the anti-clockwise direction. Means they should have only anti-parallel spin, right, or they should have only opposite spin. Then what about the other possibilities? So as we are not able to explain this, we can take it as a consequence of Pauli's exclusive principle. Whereas the other Hund's rule and Hund's rule of maximum multiplicity and half bow, which is nothing but building a principle, has clearly explained and overhead this consequence. We will explain in the next video. In this channel, I have been placing both math and science videos.